Okay, well, welcome to Chapter 3 of Organic Chemistry 1 by Wade. This chapter here is a very important chapter, if not one of the most important chapters of the course, and it's a fairly long chapter, so please stick with me and take breaks as needed. Here again is our introduction to hydrocarbons. Remember, hydrocarbons is broken down into hydro, hydrogen, and carbon. So these are molecules that are made of carbon and hydrogen only. And hydrocarbons can be classified or broken down into these categories, what are called alkanes, alkenes, alkynes, and the aromatics. Alkanes, these are all carbon-carbon single bonds. An alkene has at least one double bond between two carbons, and an alkyne has at least one triple bond between two carbons. Aromatics have these benzene rings in there that we generally don't cover until Chemistry 242, Part 2 of Organic, and so we'll go ahead and talk about these kind of compounds then. Alkanes, they have the general molecular formula of CnH2n plus 2, a very important formula. Notice how this formula works. You first look at the number of carbons, which is n, and then you can plug it into 2n plus 2 to determine the number of hydrogens that must be with that molecule. Alkanes are found in everything from natural gas to petroleum. The smaller alkanes have very low boiling points like methane and ethane, and so they are gases. Okay, substances with very low boiling points tend to be gases. And those are molecules like this one here, methane, ethane, propane, and so forth. You can see their boiling points. And notice that the boiling point starts to increase as we add more carbon atoms to it. Here are some alkane examples. Again, methane, CH4, ethane, a 2-carbon alkane, propane, a 3-carbon alkane, then butane, 4 carbons. Okay, you get up to 5 carbons, you get the pentane. Okay, and with pentane you can start getting some different isomers that we'll talk about later. The CH2 group in organic chemistry is what's called the methylene group. We say that a series of compounds that differ only in the number of methylene groups is known as a homologous series. Okay, so up here we have a homologous series of alkanes. I just start inserting more and more CH2 groups. Here again, we see that series from methane to ethane to propane to butane. Note how they fit this molecular formula. Just to go back here, so N for methane is 1, so 2N plus 2 would be 2 times 1 plus 2 for 4. Okay, come down here for butane, N is 4 for butane, so 2N plus 2 would be 2 times 4, okay, which would be what? 8 plus 2 to give you a total of 10 hydrogens for butane. And if you count them up, 3, 4, 5, 6, 7, 8, 9, 10. Here is an extensive formula-based alkanes. all the way from methane to decane, and then the list continues. What you will be held responsible for in this course are the first 10 in the homologous series. Okay, so make sure you know these names from methane to decane. Okay, and you can predict again their molecular formula by using CnH2n plus 2. Notice their boiling points increase with the number of carbons, as do the melting points. And note the density increases, but then it levels off to around 0.7 up to about 0.8. So the alkanes have lower densities than water. Remember, the density of water is 1, so that's why oil floats on top of water, because it has a lower density. Butane, C5H10. Okay, so here it is. Note we call that N-butane, meaning normal butane, meaning what? There are no branches. Okay, when you make an isomer of butane, we get this structure here. So we could call this isobutane, the isomer of butane. We'll see a better way to name this a little bit later. Okay, but these two are what are called constitutional or structural isomers, compounds with the same molecular formula, but the carbons are connected to other carbons differently. The pentane isomers, here's N-pentane. Okay, then this next isomer they call isopentane. Then this isomer they call neopentane. Okay, but we'll again learn the proper way to name these two isomers. Okay, but note the number of isomers that pentane can have. And so here we get to the correct naming system, or what's called the nomenclature system of alkanes. It's called the IUPAC, which is a conference that met several decades ago that came up with a systematic naming system for alkanes. And so you can see IUPAC stands for the International Union of Pure and Applied Chemistry. And so it's a standard method that is used internationally or universally to name compounds. And one of the key things that we'll see is that it uses the longest chain of carbons as the main chain. Okay? And common names are kept. Okay? So what are the rules? Okay, there's a few rules. The first rule is to find the longest continuous chain of carbon atoms. Okay, and then we'll use this name of this chain as the base name of the compound, or something that we will call the parent chain. Okay, so very important. This longest continuous chain of carbons from one end to another is what's called the parent chain. Rule 2 okay, can't erase that there, but Rule 2 says the number of the longest chain beginning with the end of the chain nearest a substituent or a branch. Okay, we'll look at that later. And Rule 3, we name the groups attached to the longest chain as alkyl groups. And we give the location of each alkyl group by the number of the main chain carbon atom to which it's attached. Okay, this is really complicated statement here. If you watch my video lecture online, I make this much more simpler. So let's go ahead and apply and simplify. Okay, and then we see that we write in alphabetical order all the alkyl groups. Okay, so here we're going to find the longest chain, or what's called the parent chain, using Rule 1. Okay, so here is this molecule, and we note the longest chain is right here. We then number this parent chain closest to the first branch. The first branch is this thing here. So 1, 2, 3, first branch. If I would have numbered from this end to start with, 1, 2, 3, and 4, that would have been a higher number. So this is the proper sequence of numbers. Okay, so on the third carbon I have a CH3. Remember, a CH3 group is called the methyl group, and so the full name is 3-methyl with the parent chain hexane. Okay, here's some more examples. Okay, here they circled this parent chain here, but this parent chain is not right. 1, 2, 3, 4, 5, 6, 7. Another way is 1, 2, 3, 4, 5, 6, and 7. Okay, so which parent chain is right? Well, it's this one here, where I get a total of 4 branches as compared to 3 branches. Okay, so if I have a tie with my parent chain, the way I break that tie is I choose the one with the most branches. Now, if they have the same number of branches, then it doesn't matter which one you circle as the parent chain. Okay, so this is a very important rule that you do not want to forget. Numbering the parent chain, or what they call the main chain. Okay, again, you number the longest chain beginning at the end of the chain closest to a substituent or a branch. Okay, so here if I start from this end, 1, 2, and 3, first branch. If I start from this end, 1, 2, first branch. So this would be the correct way to number this parent chain. Okay, and then if you look at labels each of these groups, so I have a 3-ethyl. Okay, I put the E before M, and then I have methyls on 2, 4, and 5. So I have a 2, 4, 5 trimethyl parent chain heptane. Okay, so here naming alkyl groups. Okay, so make sure you know these: methyl, ethyl, propyl, butyl, and the pentyl groups. Okay, so starting with 3 carbons, we start getting isomeric branches. You can have a propyl, or I can have the parent chain attached to this middle carbon, which would be an isopropyl group. Note it looks like a fishtail. Okay. The butyl has a lot of isomeric groups. Okay, so you can have the regular butyl, or you can have the isobutyl. Notice the fishtail again, but it just has an extra carbon, a CH2 attached. The sec-butyl, the attachment to the parent chain is on a secondary carbon here or here, or you can have the T-butyl group where the parent chain's attached to this carbon that has these 3 CH3s on it. So we call it the tert-butyl or the T-butyl group. Okay, or another way to look at it, kind of looks like a T, doesn't it? Okay, so applying the naming rules, name the groups attached to the longest chain as alkyl groups. give the location by number, write the alkyl groups in alphabetical order. Okay, so here where would I start numbering? This end, 1, 2, 3, 4. Okay, so I have a 4-ethyl and a 2-methyl hexane. And there it is. Okay, note the E comes before M, so we don't put them in order of number, we put them in alphabetical order. Okay, when you have two or more of the same groups, we use di, tri, tetra, and so on. So here we have a 2, 3, 4, a 5, 6, 7. Okay, so a 2, 5, 7 trimethyl. There's the numbering. And decane is the parent chain because I have a total of 10 carbons in that parent chain. Okay, so here we're going to draw some structures of 4-isopropyl octane, 5-t-butydecane. Okay, so just putting the isopropyl group here on octane and the t-butyl group on decane. Complex substituents, these are a little bit tricky, but they're not too bad. If you look, if I had this whole group here attached to the parent chain, how would I name this as an alkyl group? What I do is I look at the longest chain in this branch, which is a 3-carbon chain, okay, because this is where it's attached to the parent chain, so I don't go up here. Okay, and then I have a methyl and an ethyl here. Okay, the ethyl is on carbon 1 and the methyl is on carbon 2, so I'd have a 1-ethyl 2-methyl propyl group. Okay, same thing over here. I would have a 1,1,3 trimethyl butyl group. Okay, so here is a problem. Can we find the parent chain in this thing here? Okay, so it's looking like I'm maybe coming up this way. Okay, so we have an octane, and then we have this isopropyl, then we have 4 methyls for a tetramethyl. Degree of alkyl substitution. Okay. Come back here. Again, they're looking at complex substituents and putting them into molecules. So on the 5-carbon I have this very big complex substituent, okay, which is a propyl group that has a methyl and an ethyl on it for this complex substituent. Boiling points of alkanes. Okay, so the normal alkanes or the straight chain alkanes always have higher boiling points than their isomeric molecules do. Okay, because when you create isomers, we create branches, and branches make the molecule spherical, which make it have fewer contact points, and so they tend to have lower boiling points. Okay, here's the melting point of alkanes. Okay, the even numbers of alkanes tend to have higher melting points than the odd numbers, okay, because they can pack better. Okay, and here are those points highlighted here. Alkane sources, okay, one of the main sources are petroleum, okay, and what we do is we take them and do fractional distillation, which separates them into mixtures of alkanes that have different boiling points. When we crack alkanes, what we do is we heat them with hydrogen gas, and that breaks down the alkanes into shorter chain alkanes. Okay, so these are examples of catalytic cracking or hydrocracking of alkanes. Methane representations. Remember, methane is CH4, so we can write it with this three-dimensional picture. A wedge comes out, dash goes behind, and these two are in the plane. Bond angle 109.5. Okay, we can use stick and ball to draw the same thing. Okay, and here's another type of model set that's often used that doesn't have any spaces. Okay, so remember that methane is tetrahedral with sp3 hybridized carbon. Ethane, we can do the same thing. Okay, stick and ball model to try to show this in its three-dimensional picture. Okay, where we have two sp3 carbons, and now we can rotate around the carbon-carbon sigma bond. And this introduces us to conformations. Okay, so conformations are the result of rotation about a carbon-carbon single bond. Okay, that's what we want to start looking at. So the simplest one is ethane, where we can rotate around this sigma bond. Okay, so what we're going to do is keep one carbon still and rotate the other carbon. And when we do that, we get what are called conformations. And how do we look at conformations? Well, if we had our eyeball here and look down this carbon-carbon bond axis, okay, we can do so and try to see how the hydrogens are in relation to each other. A better way to do this is using a Newman projection, where here these three lines intersect to give the front carbon, and the big circle is the back carbon in relation to the eyeball, and then we can put the hydrogens on those two carbons. So the Newman projection is the best way to look at conformations of a molecule, and it will help us to look at the stability of them. So we can start here with ethane. Okay, what we do is we look at the maximum and minimum energies. Okay, the minimum energy is always the staggered conformation, where the hydrogens are staggered from each other by 60 degrees. The highest energy conformation is the eclipsed, where the hydrogens are eclipsing one another, so there's 0 degrees there. So if we start with an eclipsed conformation, it's a high energy, and then go down to a staggered conformation for a low energy, and then we just keep alternating between the two. And we can see the energy between the two conformations is 3 kilocalories per mole. Okay. If you look down here at room temperature, this energy barrier is easily overcome, and so at room temperature ethane is rotating very rapidly. Propane can do the same thing. Here's the carbon-carbon bond axis. So here's the front carbon, which is this carbon, and the back carbon, which is this carbon. Now this back carbon has this CH3 on it, and so we draw that CH3 here. Okay? And then we can continue and do our bond rotations. And so here they do that. Okay? They rotate between eclipsed and staggered. This time the energy difference is just a little bit higher at 3.3 kcals because I got a bigger group here, a CH3. If you remember in lecture, we have seen what's called torsional strain. Okay? Torsional strain is the strain here between the eclipsing groups, okay, where it's the interaction of these bonding electrons. Butane, okay, for butane, now we have two CH3s on each of the carbons. Okay, so those CH3s can be right on top of each other. This will generate a lot of steric strain. Okay, so remember, steric strain is two non-hydrogen groups getting close to each other. Sometimes we call that bumping strain. Here the gauche conformation offers some steric strain, not as much as the eclipsed. And then down here in the anti-conformation, the two CH3s are opposite, and so there's no steric strain. So this should be the lowest energy here. And so we see that. Okay, so the lowest energy is the anti. The highest energy is this eclipsed, where the two CH3s are right on top of each other. Okay, and the other eclipsed, the CH3s are not right on top of each other. And the two gauches are a little higher in energy than the anti, because these CH3s are starting to get a little bit closer to each other to give us some steric strain. Okay, so here we see a picture of this steric strain in that one eclipsed. Okay, so steric strain is a repulsion strain of two non-hydrogen groups getting close to each other. The cycloalkanes, okay, another class of molecules, they go by this molecular formula of CnH2n. So we take away two hydrogens from the alkane. So we see that here with cyclopropane, 3 carbons, 3 times 2 would be 6, and indeed we have 6 hydrogens on each carbon. Okay, so with the cyclic alkanes, all we do is we put cyclo in front of the number of carbons in the ring. Physical properties of alkanes: they're nonpolar, since there's no electronegative atoms in there. Relatively inert. Boiling point and melting point depend on the molecular weight. Okay, here we see the boiling points increasing, melting points generally increasing, okay, and the density around 0.7 to 0.8. Cycloalkane nomenclature: all we do is we look at the alkyl group attached, which is an ethyl, and so we would have ethyl cyclopentane. If there's only one group, there's no need to put a number on it. So we get our molecule here. Note, if there are 2 or more branches or substituents, then we must number them. Okay, so here I could start with either one. And so I'd have a 1,3-dimethyl cyclohexane. Here, I might want to put that as number 1 because the two branches are there to give those two lower numbers. So I'd have a 1,1-dimethyl and a 3-ethyl cyclohexane. Sometimes you can have cyclic groups, okay, as substituents, okay. Geometric isomers, okay. Here, when I have two groups on the cyclic molecule, I've got to tell you if they're on the same side or if they are on the opposite side. If they're on the same side, using two wedges, they are cis to each other. If they are on opposite side, using a wedge and a dash, they are trans to each other. So I have the cis 1,2-dimethyl cyclohexane. I could also have the trans 1,2. Here I have the trans 1-ethyl 2-methyl cyclohexane. Now we're going to talk about stabilities of cycloalkanes. Okay, the most stable cyclic alkanes are the 5- and 6-membered rings. Okay, carbons are sp3 hybridized, and so they require an angle of 109.5. Okay, so when it does that, it will not have angle strain. When it cannot do that, it will have something called angle strain. Cyclopropane is an example that has angle strain that we'll take a look at. Okay, and a guy named Bayer first figured this out. Okay, again, torsional strain is when we have bonds that are eclipsing. So here's a cyclopropane. The bond angles are 60, okay, but sp3 carbons like 109.5. So here I have a lot of deviation from 109.5. So this thing will have a lot of angle strain. Okay. This has so much angle strain that these bonds are actually bent, or sometimes called banana bonds. Okay, here we see the model of cyclopropane. Cyclobutane gets a little better. The bond angles go up to 90. So not as far from 109.5, and we have some eclipsing strain from neighboring bonds to hydrogen. So here we have both angle strain and torsional strain to make this cyclobutane not very stable. So as a result, it likes to bend, not be flat, to get rid of some of the eclipsing strain and help out with the bond angles as well. So as we'll see, molecules tend not to be flat in their cyclic structure to relieve this ring strain. Cyclopentane gets a little bit better. The bond angles are a little bit better, and we can get rid of a lot of the eclipsing strain or torsional strain. Cyclohexane is the best. Cyclohexane adopts what's called a chair conformation. in this chair conformation. It's called that because it looks like a chair, somebody laying down in one. And the bond angles all turn out to be a perfect 109.5. And here is the Newman projection of cyclohexane. Here you see the 6 carbons, 1, 2, 3, 4, 5, and 6. And note that all the hydrogens next door are staggered. So this thing has no ring strain, has no angle strain, and it has no torsional or eclipsing strain. Cyclohexane, very special, is strain free in its chair conformation. Okay, so here are facts that we just highlighted. It can also adopt what's called the boat conformation, where 2 sides lift up toward each other. When you do, these 2 internal hydrogens, called flagpole hydrogens, can get a little close to each other. Okay, and can bump a little bit. So you can also have a conformation called the twist boat, where it twists a little bit to get rid of these flagpole interactions. Okay, so the twist boat has fewer eclipsing bond interactions and less interference between flagpoles. So the twist boat is always lower energy compared to the regular boat. Here we see the conformational energy diagram of cyclohexane. Note we start in the low energy chair conformation, and then as we go from one chair to the other chair, we have to go through a half chair and then 2 twists and then a regular boat and another half chair. Okay, costing us a total of 42 kilojoules to do that. But here is the important part that we want to talk about, what are called axial bonds and equatorial bonds. Axial bonds stick up or down on an axis. So all the red hydrogens are axial bonds. Equatorial bonds stick out toward the equator of the molecule, and they're all in green. So you can see it on this line bond structure, you can see it on this molecular model, and on this space filling model. So here we see the chair-chair interconversion. If a CH3 here starts axial, upon it doing a ring flip, it will be equatorial upon the ring flip. Okay? So axial converts to equatorial, equatorial converts to axial upon the ring flip. Okay, very important rule. Alright, here we see it again. What they're doing in this structure is showing it in the Newman projection. Here showing that CH3 being gauche in the axial position, and gauche over here. But when the CH3 gets ring flipped to the anti or to the equatorial position, note the equatorial gets me away from these CH2s, and so it's a much less energy conformation, much more stable. Okay, again, remember the equatorial position is always the most stable position. Okay, so between these two, this would be a much more stable conformation by 1.7 kilocals per mole, because the CH3 is in the equatorial position, and so alleviates what's called the 1,3 diaxial strain. See it even more with the T-butyl group. Okay, put the T-butyl group in the axial, you get a lot of crowding here. But put it in the equatorial, that crowding is relieved, and so this would be the more preferred conformation. Okay, so again, substituents are always less crowded in the equatorial position. Now, what happens if we have two groups on the cyclohexane ring? Here is cis 1,3. Okay, so note I draw this little plane here, top, so these two are cis, so I can have them both being axial, or upon the ring flip they both go equatorial. So this conformation here would be the much more stable one compared to this one. When I look at the trans, here the trans, I have an axial methyl and an equatorial methyl. Okay, again, trans, there it's bottom, there it's top, so they're trans to each other. When I do the ring flip, they still stay equatorial and axial to each other. So both of these chairs turn out to be the same energy. Let's go to the cis 1,4 di-T-butyl cyclohexane. Okay, so here bottom, bottom, okay, and note that what they're doing is looking at the twist boat and how that helps to alleviate some of the strain. Just some sample problems. Here they want you to draw the most stable conformation of trans 1-ethyl 3-methyl cyclohexane. Okay, so here they're trans, top, bottom. But what's the difference? Well, this smaller CH3 is equatorial here. Here this larger CH3 is equatorial here. So if I have to make a choice, always choose the larger group to be equatorial, and that will give you the more stable conformation. Here are some bicyclic molecules where I have two rings fused to each other. Okay, and so we can have bicyclics. We can also have the spiro compounds where they're joined at one carbon. Okay, the bicyclics are joined at two carbons. Okay, so remember how we named those. Bicyclo, you put bicyclo first, then you look at the bridgehead carbons and I count to them. So 1 carbon, 2 carbon, 3 and 4, back to the other bridge. So 4, this way 4, then this way there's 0 between them. So this would be bicyclo 4,4,0 decane. It's decane because the total number of carbons in the whole molecule is 10. Here this bicyclo, if I go this way, is 1, 2. This way 1, 2, and this way 1. So I have a bicyclo 2,2,1, total number of carbons 7 for heptane. Okay. For the spiro, I indicate it's a spiro. Then I count the number of carbons, 1, 2, 3, 4. and this way 1, 2, 3, and 4. So spiro 4, 4, and then the total number of carbons is 9, so I have nonane. Okay, so here they take you through that procedure of how to name bicyclos. Okay, always remember to put these numbers in decreasing order. Okay, here's decalin. Okay, you can have cis or the trans. Okay, the trans is more stable because the alkyl groups turn out to be equatorial. And that's the end of our recording.